All right. So now let's look at the second major component of the data preprocessing step, which is data integration, right? Okay. So the data integration has the following, issues, right? The first issue here is entity identification. This is just a problem of identifying object instances from different databases, assuming that you're getting data from different databases, and then trying to correspond them to the same real world entity. We're going to see an example of this. Okay. Another issue here is redundancy and correlation analysis, right? Where we can do different treatment for both nominal attributes and numeric attributes. Okay. So other issues you might encounter in data integration is duplicate attributes. Okay. We also have data value conflict detection and resolution. And then also you might add here irrelevant attributes. So I'll just abbreviate that, irrelevant attributes. Okay. So a good example I can think of right now is, let's say if you have student ID, right? So we have student ID and maybe GPA. Okay. So we may say that this student ID is an irrelevant attribute, right? It doesn't influence the calculation of the GPA. Okay. So we can remove it from our table because it doesn't influence the calculation of the GPA. Okay, so that's an example of an irrelevant attribute. All right, so suppose maybe you work at Maya, right? And you're analyzing, you receive like 2 CSV files from probably Lansing and also maybe Grand Rapids branches or stores, right? Okay, and then those 2 different data sets, right? They come in and one has customer number and the other one has a customer ID, right? Now, during integration, now you're bringing this data from multiple sources, right? Okay, so one of the challenges is that the data may become redundant, right? So in other words, we're saying the custom ID from one database in probably Grand Rapids and the other one custom number probably from Lansing refer to the same attribute. What if these attributes have the same value, right? So when that happens, this becomes an example of entity identification problem. Okay. Sometimes when you don't have just an extension of that, sometimes when you don't have when you don't have a key that is defined, this entire attribute can end up being the primary key. Okay, something you just keep in so you can keep in mind. Another example we can look at. So let's say we got these 2 databases, right? So one entity, the person, right, is coded as Bill Clinton, right? In another database, we have the same name here, William Clinton, right? They might look different, but we're talking one and the same person, right? So as well, this is another issue of entity identification problem. Okay. So examples of metadata that we can add for each attribute is, you can include name, meaning of that attribute, data type, whether it's a string, an integer, float, and all that, range. And in most cases here, if these attributes, okay, you can have null rules, right? You can put null rules here to handle blank or missing values or null values, right? Okay. Now, the reason why we have metadata here, this can help us avoid errors during schema integration, right? If you've taken a database course, you realize you can enforce that via enforcing functional and referential constraints. Okay, impose that on your schema, database schema. That way, you'll avoid some of those errors during schema integration. Okay. And lastly, I could provide you another example here. Let's say you want to transform the data, right? The metadata from two databases, right? So one database here. So we have one database here, let's say A and B. Okay. So this database, right? We has this attribute, pay type. Okay. Let's put an underscore there, just make it elegant. So on one hand, we have this database has H and S, right? Meaning hourly and salary, right? Then in this database, right, we are using also for the same pay type, we're using 1 and 2. Okay. So these are another good example of entity identification problem, right? So, and this is something you might try to address during data cleaning, okay? A process that we've already looked at. This would be a good candidate for data cleaning. So you may need to decide how to encode that data to make that consistent, okay? So at the end of the day here, entity identification allows you to sort of understand what attributes, okay, you need to, take care of so that, you remove those redundancies. All right. So in addition here, I can also add that during other things that are related to entity identification problem. So we have synonym and homonym. So we have synonym. Okay, so if you're actually in the field of text mining, synonym, how do you write this now? Synonym, right? And we have an issue of homonym. Okay, so we have homonym. Okay, these are common problems too during entity identification. So suppose you have two different employee numbers assigned to the same employee in different tables. Okay, that constitutes a synonym problem. Again, when you have different employee numbers, right, assigned to the same employee, okay, in two different tables, that's a good example of a synonym problem. On the other hand, when you have the same employee, right, we have a same employee number in two relations for different employees. That's a good example of homonym. Okay, so again, just get the distinction between the two. So homonym means you have an employee number in two different relations. Relation is just a table 1 and table 2. So what we're saying with homonym here problem, say employee number in two relations for different employees. Okay. All right, so far so good. So the next issue we want to address here is redundancy and correlation analysis, right? And there are two things here we can take care of. So we can, when we have variables that are categorical, we call that nominal, or when we're dealing with variables that are numeric, right? So there are different approaches we can use to take care of that. Okay. So, but again, let's look at what this redundancy is, right? Redundancy or redundant data really occurs while we merge data from multiple databases. Again, some of these issues occur when you're getting data from different databases, right? So if you don't remove this redundant data, right? If you don't remove this redundant data, definitely you end up having incorrect results, right? During data analysis, right? Okay, and we've already looked at one issue here, object identification. We've already looked at this before. Okay, object identification from the previous slide. Okay, object identification. Okay, the second issue here with redundancy is what we call derivable data. Okay, meaning that one attribute can be derived from another table. Okay, so let's look at an example here. So suppose you have a table that has a daily revenue, monthly revenue, and yearly revenue, or in our case here, it could be annual revenue, right? There's an abbreviation there. Okay, so from here you can see, given this monthly revenue, right, you can easily, derive or get the annual revenue. Or if you get the daily revenue here, you can actually compute the annual revenue, right? So question is, do we need all these three variables, right? We can discard either of this, right? Given one, we can derive the other. So there's a bit of redundancy here. So you need to know, in fact, redundancy is all about how to understand what variables to throw away, that are redundant, basically, okay? And it's a process, okay? So how do we really determine that? So we have different techniques to determine variables that are actually correlated. So one approach is to perform correlation analysis, which means how strongly one attribute implies or is kind of influencing the other attribute, excuse me. Okay. And for nominal attributes, we can perform chi-square test, right? And for numeric attributes, we can perform correlation coefficient, right? And covariance. In this slide or in this video, I'm just going to show you how to do the chi-square test and correlation coefficient. So let's look at chi-square test, right? So this is a special kind of correlation, all right? Whereas correlation, looks at numeric attributes, chi-square will take care of nominal variables, or what we call categorical. Okay, so given this contingency table, we have, gender and preferred reading, right? So the goal here is to come up with a hypothesis, right? Our null hypothesis is, are gender and preferred reading, are they related? Are not related? So that's actually a null hypothesis. So we have male here, female, fiction, and fiction. We have this data, okay? So the next thing we want to do is to compute based on this formula, right? Now, to do this, so here E11 means first row, first column. First row, first column is 250. For now, just ignore this, all right? Ignore this because this is what we want to compute. This is the expected value, right? So the actual value is 250, right? So the total number of male here is 300. Total number of multiplied by the total number of fiction. Fiction here is 450. So that's how we get that. Divided by the total number of the population, number of people, right? So we get 90, and that's how we get this, okay? You do the same for all the others, right? So if we pick an example here for this one, so here will be what, right? So row column, right? That'll be row 2, right? Column 2, okay? So you get the total number here for female. So here we'll just change to female. That'll be 1,000, right? Sorry, 1,200, right? Then, so if you're doing column 2, row 2, then multiply by 1050, divide by 1,500. You should be able to get 840, okay? So you do all that and you should be able to get all these numbers, right? And then how do we get our chi-square value? So we just get the difference between the actual and the observed, actual, observed, and then we add them all up together. That's why we have 250 minus 90 squared divided by the observed here, all right? We do that for all the others. So up to here, 1,000 minus 840 squared divided by 840. We get that, and then we get this value, okay? Now, once we have this value, then we kind of look at the chi-square table. So we want to compute the degrees of freedom. So the degrees of freedom here, in this case, essentially we use this formula, right? So we just be the, so the row here, -1, right? Okay, get the product of column -1, right? So incidentally, this is a 2x2 table, all right? Meaning we have 2 rows, 1, 2, and 2 columns, 1 and 2. Okay, this is just the total. Okay, you can add just to make it things easier. Okay, so if you plug it here, it will be 2 minus 1, 2 minus 1, right? That gives us what? Degree of freedom of 1. Okay, so if we now look at, so we go to our, if you're coming from statistic background, if you have a statistic background, took a statistic class, then you realize when we look at the degree of freedom, okay, and we find this value here for the chi-square, find for this value for degrees of freedom, okay, we'll find that it's 10.828, okay. Then we compare with our value here that we found, right, 507.93, okay. This is far much greater than what we have here. So what we do now, we can now safely reject our null hypothesis, which was gender and preferred reading is not related, okay. So what that means, gender and preferred reading are actually related, right? In this case, they are strongly related, okay, meaning that I could just use male or female independently because one or the other will give us the similar results. So in our case here, we can reject the null hypothesis that gender and preferred reading are independent and conclude that the two attributes are strongly correlated for the given group of people. And that's chi-square, okay? And when we look at nominal attribute, we could use correlation coefficient, okay? Correlation coefficient is given by this formula, right? You can, use this formula, or you can actually, use scatter plots just to visualize whether they are positively correlated, right? Positively correlated or no correlation, okay? In fact, here, no correlation or negative correlation, right? Okay, but really, let's quickly just look at what this formula means, right? Let's say we are looking at two variables, right? We have age, okay, and we have GPA. Okay, in some books, you'll find that they call it CGPA, right? So the denominator here, all right? So let's look at this. This standard deviation of A, let's say A here equals to age, okay? Then standard deviation, the sigma of B here, let's say B here equals to GPA, right? And then N minus 1, N probably is the number of students in our class. For example, let's say N here in our case will be N equals to 30, okay? So you plug it in there and you get, get the sigma, standard deviation for age, and standard deviation for B. That makes our denominator. Now let's look at our numerator, right? So A1 here minus A bar means here the mean. So A1 here means each individual student in our class, right? Let's get their age. Assuming that probably the average age in our class here, in the class here is maybe 21, okay? So let's say Jane is 17, so just say 17 minus 21. John is 18 minus 21, right? And you go on and on and on for all the different combinations here for all the 30 students, right? Multiply that by, let's say, the average GPA here is 3.0 for B, but for that, right? The mean there is 3.0, right? And let's say Jen was doing really well. The average got GPA of, and you have to correspond that together. So GPA of 3.9, that'll be 3.9 minus 0. So you do all that and add them all up. So for all possible combinations, so from 1 all the way to N equals to 30 for all the students, you compute that. And then you get that value. Then that value is what will be the correlation of A and B, okay? So once we have that, then we can now look at here. So if the correlation there, if that number, right, if that number is greater than 0, then we say that A and B are positively correlated, okay? And we can go here, we can see here, what that means, an increase in value in age also corresponds to a value in GPA. Let's say we have GPA here and age here, okay? So we can see here in the last quadrant here, or last row here, all these values, show some tendency to positively correlate. An increase in Y, there's a resultant increase in X, okay? And then here, so if the correlation here, the value here equals to 0, that means they're independent, right? No correlation. And you can see here, there seem not to be any correlation here within the data points. It's just jumbled up. And then lastly here, If it's less than 0, then what that means, negatively correlated. So let's look at here, right? That means we have a negative slope. Just remember that. That means an increase in y, there's a decrease in x, as long as you have a negative slope. Okay. Or alternatively, you could say also a decrease in x results in an increase in y, or a decrease in y results in an increase in they should be like this. An increase in x. So basically, it's just negative slope. Okay, and that's correlation analysis. But remember, correlation is not causation. Okay, all right. And here's an example here. Let's say the number of hospitals and the number of car thefts in the region are correlated. So if you're told that, okay, so what does that tell you? Okay, does that mean that one causes the other? So that's the question we're asking here. Okay, so in research, it might not be very clear cut. Might be not a cookie cut, simple as that. So most times, there could be a confounding variable. All right. So this confounding variable is what we refer to as a third variable. Okay, this third variable may now cause this causation, right? In our case here, this third attribute, okay, probably namely population, okay, is what is causing this increase in the number of hospitals and the increase in the number of car thefts, right? But just given hospitals and the number of thefts might not tell us really what's happening. There's correlation, but it's not causation, meaning one does not influence the other, but there has to be a third variable. Okay. Sometimes in research, we call that confounding variable that actually causes or links these two. Okay. So keep that in mind. And then lastly here, as we conclude, the other issue in data integration is data value conflict detection and resolution. I think we've already looked at this before, but I'll quickly mention here. So if you're working for a regional store, you realize in the States, we use pounds. Elsewhere in the world, we use kg, right? Or maybe gallons. The rest of the world, they use liters, right? So this might cause some identity issues, right? So how do we detect and try to resolve that? Okay. So essentially, you just want to make sure you resolve those conflicts. Try to harmonize that so they're in the same kind of metric. Okay. So the story so far, we've already looked at data cleaning, right? What is data cleaning? We've looked at techniques that we can handle manage missing data. We've also looked at some of the techniques we can handle noisy data. Okay. Like here we've talked about removing the tuple, regression and so on and so forth, right? And then also data integration. We've looked at the issues that you may encounter, like entity identification problems, right? We've looked at how to detect redundancy. We've looked at correlation here for numeric attributes, right? Numeric attributes, and here chi-square for nominal attributes. So we've all looked at that. And what is important here, always remember, correlation is not causation. Okay. So very important. So just be careful that during integration, it just helps to reduce and avoid redundancies and inconsistency. All right. So in our next video, we're going to be looking at data reduction. Thank you.